Hello. So welcome back to MIN720 pattern classification. Uh, we were These are the new videos for the remote lectures, and we'll pick off where we left off in class before we were so rudely interrupted by the coronavirus. I'm sorry that this video is a couple of days late. It took me some while to get over the technical stuff and figure out how I'm going to do this. Hopefully, this will be our new format. I'll explain over the slides and draw on the slides, so the slides will be both slides and Blackboard. And also, time to time, we'll go back to Jupyter to try the things we talk about here. Okay, so if you remember, we talked about dimensionality, the curse of dimensionality, how when the number of dimensions gets too high, you suddenly have a space where nothing's close anymore, so nothing's similar. It's difficult to determine similarity between data objects, between instances, which makes all the downstream stuff you're supposed to do, like clustering, classification, and what we're interested in, pretty difficult. So what we have to do is essentially figure out a way when you have a very high dimensional data set to get rid of those dimensions. So one thing you can do is, like we talked about before, you can trust an expert. If you have lots and lots of dimensions, like you have a gene expression data set with thousands of genes, they can let you pick what's important. Right, so the expert can come and tell you, okay, if you're trying to say look for breast cancer, then all you're interested in are these 50 genes like PAM50. Otherwise, in other domains, there'll be a domain expert that will tell you which of the hundreds and thousands of features or tens of features is relevant to your classification task. Another way is essentially trial and error, gain-based feature selection. So you build a classifier or a cluster and you pick different subsets of, so trial and error, you pick different subsets of features and see how well they classify your data, or how well they cluster your data, alternatively, and you pick the one that has the best results, namely the best gain. And the last form is essentially what we call distribution-based feature selection, where you look at how the data is distributed over the space and only kind of pick the dimensions where the distribution is most pronounced. Namely, we picked a dimension where there's a lot of variance, right? So if your data varies very little in one dimension, but varies a lot in some other dimension, then the second dimension is obviously a better choice. So what we talked about was PCA. Obviously, we first kind of eased ourselves into the idea with what's called the Mahalanobis distance. We talked about the covariance matrix, how it's built, etc. Kind of refreshed our knowledge on that. And we talked about the Mahalanobis distance, which is normalized, essentially a distance that's normalized against, let me go back to that slide, sorry. Okay, that's normalized against how the data is distributed. So we found out that if you and it's not we use the covariance matrix. So if the covariance matrix says that the variance is most in this axis, and most covariates are kind of dependent on each other, so that you get this nice positive correlation type of distribution, then a distance between these 2 points, between A and C, isn't as big a distance as the distance between A and B, because the distance between A and B cuts across the grain, so to speak. So it's a more important distance. And one example would be, for example, this might be uh, uh, the engine size of a car, and the other dimension might be, for example, its gas consumption in liters per kilometer or 100 kilometers, whatever you want. The numbers don't matter. And this is what you expect, right? So smaller engine cars tend to have lower consumption, and cars with larger engines tend to have more consumption, tend to be more gas hungry. So if you have these two cars, they're typical examples. A is a smaller car, a smaller engine that consumes less, and C is a larger engine that consumes more. So that's not very interesting. However, for example, B is a smaller engine that consumes a lot more gas, a lot more petroleum. So the distance between A and B is more pronounced in the Mahalanobis distance than it is than the distance between A and C is. So that was the idea. From there, if you remember, we talked about PCA, uh, principal components analysis, which is essentially, you can think of it as generalized Mahalanobis, right? So instead of distances, it rotates the space you're in such that the basis vectors, the x, y, z coordinates, or however many coordinates you have, are aligned such that they are on the axis of the highest variance. And we said that if you have, for example, a two-dimensional data set, the first principal component, the first axis, is the one that has the most variance, and the second axis is perpendicular to that or orthogonal to that, and has the next highest variance. If I just jump there, let's see if I can get this right. Yeah, in summary, so we had, if you had a data matrix X, uh, which is an n by n matrix, n being the number of examples you have, the number of instances, and m being the dimensionality, the number of features. You can put those numbers obviously in this matrix X. And let's say we have x prime, which is the centered version, the normalized version of x, such that each dimension has a mean of 0. Obviously, this is easy to do. For each dimension, you take the average and shift everybody to the right or the left or higher or lower, depending on what the mean is, so that you get a mean of 0. The interesting thing that happens then is when you have that kind of centered data matrix X, if you multiply it with its own transpose, you get the covariance matrix. And that makes sense, right? Because if you look at the definition of the covariance matrix, if I can find it, somewhere here, I think. No, let's see. There we are. Notice that the covariance matrix is essentially the data items xi, xj, so the different dimensions, the different columns of the X matrix, each one is you subtract the mean. So if you've already centered this dimension, then the mean is 0, so you're subtracting nothing, which means it's essentially the multiplication of these things and the expectation of the multiplication. So matrix multiplication conveniently does that for you. So if mi is equal to 0 for any, well, rather all dimensions. What happened there? Okay. For all dimensions xi, so for all of your dimensions, if the mean for that dimension, mean value for that dimension is 0, then you're good. Essentially, multiplying x with itself will give you the same thing as taking the expectation of the differences, the multiplication of the differences of the means. So that's convenient. Going back to PCA, so we have the covariance matrix. And we said that to find the right rotation, essentially, remember we actually derived all this in class, so I'm not going to go back into it. But it turns out that what you have to do is essentially do the eigendecomposition of the covariance matrix. So when you look at it, you get a vector of lambdas, the eigenvalues, and matrix of eigenvectors. And you look at the eigenvalue with the highest eigenvalue, and that essentially is the dimension in which the data is most stretched, so to speak. Now, if you're not comfortable with eigenvectors and eigenvalues, you can obviously go to look at some of the references for linear algebra, but another good source, an intuitive source, is 3 Blue 1 Brown's videos on the matter. I'll put links if I can onto this video as a card, or if I can't, I'll put the link down in the comments so you can go watch those if you're not kind of really familiar with this stuff, or even just for fun, because they're very nice videos. Okay, so the eigenvalue that's highest gives you the eigenvector that has the most stretch, so to speak, the highest variance. So that's your first eigenvector. So and then the next one is the second eigenvector. Obviously, for example, if sigma is a 2 by 2 matrix, which means m is equal to 2, you have 2 dimensions, then w is again a 2 by 2 matrix. So it's essentially 2 vectors, one of which is the first principal component, the other is the second principal component, and you decide what's the first principal component depending on which one has the higher corresponding eigenvalue lambda. Okay, so, and the idea was, once you have those, then the first eigenvector would essentially be the first principal component will essentially be the eigenvector for a new, so to speak, x dimension where there's most variance, and the second one would be your new your new y-axis. And essentially what you're doing here is then with PCA, you're finding some rotation, right? So actually you're rotating your dimension, kind of your basis vectors, your axes, such that they align with higher variance. So you can use only maybe one of them. And if you use just this one, now instead of the original x and y coordinates, if you have x prime and y prime, which are the x prime being the first principal component, y prime being the second principal component, what you have is essentially a new two-dimensional space, but with better aligned axes. So you can, for example, bring this down to a single-dimensional space by not using the y-axis, and the x-axis is still a good approximation of the data. The errors, as you can see, are kind of small compared to the original x-axis, where the errors, if you just used that axis, would have been large. And obviously, this generalizes to multiple dimensions. This doesn't have to be two-dimensional. It can be however many dimensions you want, but then you'll have that many principal components the first one will be the first axis, second axis, and so on and so forth. So this, you can use this to figure out the best reduction. And we talked about the applications of PCA. We actually looked at a few examples on Jupyter in class. But one very obvious use case is compression. So if you have data that's, for example, 10,000 dimensional, and let's say it's image data, right? So for example, you have 100 by 100 pixels of a grayscale image, which means each pixel is some value between, let's say, 0 and 1, 0 being white and 1 being black. Then your little picture of 100 and 100 dimensions is essentially 10,000 numbers, right? 10,000 dimensions. Now, if it turns out that these pictures don't have that much variation in certain regions, or kind of in certain ways, you can actually do principal components analysis and use only the 51st principal components. Now, instead of 1,000, say 10,000 dimensions, you have 50 dimensions, which means you have 1 to 200 compression. That's the first obvious use case. The second is what we're more interested in is essentially visualization. When you have data that's multiple dimensional, essentially more than 3 dimensions, we humans can't really see it. I mean, maybe 2 dimensions is nice. You can plot it on a scatter plot and look at the points. Even 3 dimensions, maybe you can plot as a surface or as a volume and see what it looks like. Maybe rotate it and so on and so forth with a computer so you can see 3 dimensions. Even 4 dimensions, you might add time and see how it changes. So it's a 3-dimensional animation now. But when you get to 5 dimensions, things start getting tricky. And if it's, let's say, 10,000 dimensions, there's really no way you can visualize how that data is distributed. So what you can do is you can map very high dimensional data down and take the first 2 to 4 principal components, and hopefully, especially if it's linearly separable, which is what we're going to talk about soon, you'll have a plot at least that you can see and make sense of. Another use is anomaly detection. Namely, if you have, for example, the case we had in Mahalanobis, where you have data that's distributed like so, and what's going to happen is, obviously, in data like this, the first principal component is going to be along the axis of the data. So if I only use this component, most points in this rotation, if I drop it down to a single dimension, most points will have very low error. However, if I have an anomaly, like the small car that used a lot of gas, then now its error is high. Therefore, you can use it for anomaly detection. And obviously, you can also use it for dimensionality reduction, which essentially as a first step before some downstream classification or clustering or whatever you're wanting to do with that data. So, and this solves the problem of the curse of dimensionality. Well, it doesn't solve it, but it mitigates it. It helps you manage it, so to speak. Okay. So the problem we left this at was the problem of linear separability. So when you kind of have data, for example, 2-dimensional data that's distributed like this, I don't know if this animation will work. No, it doesn't work. But I'll draw the same thing. When you have data that's kind of distributed like this, obviously there's some pattern to this data. I mean, there's this empty region here, and kind of the two classes of points within the two dimensions are have some way that you can actually classify them. Later on, we'll talk about border classifiers. And let's say if I had a border like this, actually, let me do this way so it'll make more sense in the future. Let's say this is our centered coordinates. So I take this data and again, centered to the mean. So this is 0.0 on the x coordinate and y coordinate, and you have this. Now the thing is, when you run PCA on this, you're not going to get anything useful because PCA will look at all the directions and the variance is more or less the same in all directions. So you'll get some arbitrary principal components. Maybe small offshoots like this will dictate what the principal component will be, but that's not going to be useful for you in separating or clustering this data. And let's say you wanted to do it in kind of one dimension, it's not going to work. So what we can do is kind of, now each point here is essentially a vector of two numbers, right? So for example, this one is x is, let's say, at 5, y is at 6 maybe, right? So this is the vector 5 and 6. Let's say I had some transformation, I'll call it phi, of some point in our data, let's call our data points x's, so this is then, for example, x 243 or something. So the 243rd point in this set of points, and that's the vector, and let's say x1 is 5, x2 is 6. So superscript is which instance it is, and subscript is what dimension of that instance. So this is at coordinates 5 and 6. Therefore, x1 of 243 is 5, x1 of 243 is 6. So this is the 243rd point, let's say, by some arbitrary way of counting these points. Okay, so phi of x, we can define it as, for example, phi of x is equal to a new vector such that it has x1, x2, so the original two dimensions, but it also has a third dimension, a fabricated dimension, a computed dimension, such that, let's say, it's x1 squared plus x2 squared. So what's going to happen to this thing is when I take x, the 243rd point, and apply this transformation to it, it's going to convert into 5, 6, and let's say 25. Square of 5 is 25, square of 6 is 36. So 55, add 6 more, 61 would be the last coordinate. Okay, and notice what this does. It essentially adds a polar aspect to our thing. So most points here, the third dimension, because they're closer to the center, the squares of their coordinates will be small. This essentially gives you the square of the radius of the point from the center. So these guys will have higher third dimensions, and these will have, the green ones will have lower third dimensions. So when you look at it, if I try to plot this data on the third dimension, so we're looking at the first two dimensions, essentially x1 and x2. If I plot them in a separate part against x3, sorry, this pen doesn't work as well as I hope. Okay, so these would probably look something like this. The green ones will be clustered here, sorry, let's do it like this. The green points will be on the x3 number line, they would be here, and the others would actually be here. So this third dimension will allow us to separate these guys. Actually, when you have your own copy of the PDF, these little buttons here, they will work and rotate this to show you the extra dimension that I talked about, and you'll be able to visualize what I'm talking about better than. Unfortunately, this PDF reader that I'm using to do the screencast doesn't allow that. So you map, like I said, our point X into a new mapping, and you get this time a separable data set, because what's going to happen is, like I said, like you'll be able to visualize later on, along the third axis over here, along the third new dimension, all the points in the middle will be on one side, and all the points that are farther away with the center will be on the other side. So whatever we've done here, we're talking about the curse of dimensionality, but what we've actually done is we've essentially added one more dimension. Seems like we made the problem worse, but in this case, we're kind of allowed to and have to make the problem a bit worse to make it better later, because the data is not linearly separable.